Today class we are going to see D and F block elements. Okay. So D block elements where it is present in the periodic table. It is present in the middle. Okay. So for left hand side, that is here now for left hand side it is S or S block elements are present, and middle the D block elements are present, and here P block elements are present. Okay. So here 1 to 18th group, the 3 to 12 D block elements are present, and period it started from first period, second. There are how many periods? 7 periods in the periodic table. First period, second period, third period, and fourth period. It started from fourth period. Okay. So fourth period and fifth period, sixth period, and so on. Okay. So like here general electronic configurations. What is the general electronic configurations? This is NS2 N minus 1D. Okay, so this is for general electronic configurations. So the D block elements we may called transition elements. So why it is transition elements? Because it's a bridging elements between S block elements and the P block elements. Okay, and also incomplete filled d orbital in the nature of state as well as the oxidation state. Okay, so incomplete filled means it is a n minus 1 to 1 into d, that is 1 to 10. Okay, so how many electrons possibilities for d orbitals? That is 10 electrons. Okay, for d9 it is a partially filled. So then only it is called incomplete filled the d orbitals, it is called transition elements. Okay, so that only for this case for zinc, cadmium and mercury. Okay, so mercury, that is a Hg. Okay, mercury, that is a Hg. Okay, right, Hg. Okay, listen. So this is started from n. This n it represent students. This n represents the number of period. So 4 minus 1 3. Okay, so 3D series. 3D series started from scandium to zinc. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Okay, and so n minus 1, that is 4 minus 1. That is 4D series. 4D series started from yttrium to cadmium, yttrium, zirconium, niobium, molybdenum, and technetium, ruthenium, rhodium, and palladium, silver, and cadmium. Okay, and 5D means that is n 5 minus 1, that is 5D, and 6 minus 1, that is 5D series. Okay, lanthanum to mercury, hydrogram, lanthanum, hafnium, and tantalum, tungsten, rhenium, osmium, iridium, platinum, irium, and hydrogram, mercury. Okay, so this is your, there are 4 major series: 3D series, 4D series, 5D, and 6D series. Okay, right, this is for your general electronic configuration. This is introduction part. Okay, so why it is called transition elements? And so the 3D series started from scandium to zinc, and 4D series started from yttrium to cadmium, and 5D lanthanum to hydrogram. Okay, now let's move on to next one, general trends. Okay, so general trends, first the atomic radii. Okay, in the first the trends is atomic or radii, atomic or ionic radii. Okay, ionic radii. So what's happened? Atomic and ionic radii. Okay, listen. So before that, earlier we studied along the period and down the group. For here, what's happening for atomic and ionic radii, whether it is decreases or increases for 3D series or the 3D, 4D, and 5D series. Okay, so first of all, the atomic radii, it is increases, it is decreases scandium to vanadium. Scandium to vanadium, scandium, titanium, vanadium. Okay, so chromium, it is the exceptional case, because chromium, its the configuration is 3D5 4S1. Okay, this is a half filled electronic configurations. Okay, After that, why it is decreases? Because its atomic number, scandium atomic number is 21, 22, 23, 24 and so on. So the left to right, which means that is a 3D series, what's happening for the ionic radii completely decreases, scandium to vanadium. After that, this is a half-filled electronic configuration, chromium, then manganese. After that, the iron, cobalt, nickel, it is a constant, then simultaneously it would be increases because of the effective nuclear charge. Why the 3D series for scandium to vanadium decreases, after it would become constant, then the iron onwards it is slightly absolutely more or less similar as well as increases the atomic radii. Why? Because of the effective, the first point is it effective nuclear charge. Okay, so effective nuclear charge means that is this is Ns outer electronic and this is N minus 1d penultimate shell and this is nucleus. Okay, so the electrons entering directly into the N minus 1d penultimate cell, Ns and N minus 1 penultimate shell. Directா வந்து Ns N minus 1 penultimate shellக்குள்ள வர்றதுனால தான் இதை நம்ம என்ன சொல்றோம், transition elements னு சொல்றோம். So effective nuclear charge means the scandium to titanium, it is only one electron added. Okay, so 21, after that 22, after that 20, so only one electron added. So it's going to the effective nuclear charge, the proton as well as the electron. The nucleus directly attracts the electrons one who present in the last valence shell. Okay, so easily it attracts so that only the atomic size decreases. Okay, after that the iron, what's happening, chromium, it is a, listen, chromium 1 2 3 4 1 2 3 4 5 half filled. Okay, so half filled. After iron, what's happening, it's a 26, it's a 6 electrons. Okay, 1 2 3 4 5 6 electron. Okay, 6 electron means here the pairing takes place. Pairing takes place means this is electron and another one electron repulsion takes place. Okay, so iron to cobalt, nickel, copper, the electron repulsion takes place, so that it is a constant. The radii would be the covalent radii would be constant. After that it is slightly increases because of zinc. What is that? That is 3s2 and d10 configuration. Okay, so zinc 1 2 3 4 1 2 3 4 5 6 7 8 9 10. Okay, completely filled. So completely filled, there is no repulsion takes place. So now here the effective nuclear charge and the repulsions are counterbalanced and the repulsions is a dominated, so that it is slightly increases. Okay, students, atomic ionic radii first decreases, scandium to vanadium. After that it is a constant. Then iron to copper, it is slightly absolutely similar as well as increases because the effective nuclear charge. After that the repulsion pairing takes place. Here the electron repulsions takes place. That is, after that electron repulsions, then the completely filled, there is no repulsions, counterbalanced with Z effective charge and F nuclear charge and the electron repulsions. So it after that it's they increase the ionic radii. Okay, so this is your radius, atomic and ionic radius. Okay, after that density. What about the second one, density? Density. So density means it is a m by v, mass per volume. Okay, so atomic number is equal to the number of protons. Okay, so scandium to copper increase the density, increase the density. So this is for along the period, okay, 3D series. What about the down the period, that is 3D, 4D, 5D, okay. So here it is as usual, atomic number increases, the radius also increases. But one thing, this is lanthanide contractions takes place here, okay. So lanthanide contractions, what is lanthanide contraction? This is lanthanum. After that only the lanthanide contractions takes place. Lanthanide contractions means that is the intervening of 4f orbitals present before the filling of 5D orbitals. இப்போ 5D orbitals தான் fill ஆகிட்டே இருக்குது. fill ஆகிட்டு இருக்கும்போது இன்டர்வீனா என்ன வருது அப்படின்னா 4f orbitals. 4f அப்போ இங்கே வந்து இப்போ இதான் நியூக்ளியஸ் அப்படின்னோன்னா, according to our alpha principle, that is 1s 2s 3s that is 5D ஆர்பிட்டலுக்கு முன்னாடி இப்போ 4f electrons ஸ்டார்ட் ஆகுது. இன்னர் transition elements 14th 4f 14 elements present ஆகுது. so that it is a intervening before the filling of 5D orbitals. so it causes the lanthanide contractions because of the more effective nuclear charge takes place between the nucleus as well as the last shell valence electron, last shell electrons, okay. so here we use the term screening effect. Why it is called screening effect? Because the intervening of 4f electron present, it is a diffused form, somewhat hiding between the nucleus and the electron. so the screening effect, more effective nuclear charge, so that it causes the lanthanide contractions, completely decrease the size, okay. so that is called lanthanide contractions. so the lanthanide contractions causes more or less zirconium hafnium is the same atomic and ionic radii, niobium and tantalum would be a same atomic and ionic radii, or molybdenum and similar atomic and ionic radii because of lanthanide contractions. It is a one more question, okay, because of lanthanide contractions. lanthanide contraction ங்கிறது என்னன்னா 5D வந்து fill ஆயிட்டு இருக்கும்போது இன்டர்மீடியட்டாக யார் வந்து உள்ள கரடி பூந்த மாதிரி யார் வராங்கன்னா எஃப் ஆர்பிட்டல் எலக்ட்ரான்ஸ் ஃபில் ஆகுது. அப்போது நியூக்ளியஸுக்கும் எலக்ட்ரானுக்கும் வந்து என்ன செய்யுது, சம்வாட் ஸ்க்ரீனிங் எஃபெக்ட். ஏன்னா அங்கங்கே டிஃப்யூஸ் ஆகியிருக்கு அந்த எலக்ட்ரான்ஸு. அப்போது நியூக்ளியஸ் வந்து என்ன செய்யுது, லாஸ்ட் எலக்ட்ரானை வந்து அட்ராக்ட் பண்ணுறதுக்கு த மோர் அட்ராக்டிவ் ஃபோர்ஸ். அப்போ எஃபெக்டிவ் நியூக்ளியர் சார்ஜஸ் வுட் பி மோர். அப்போ தட் இஸ் ஹைலி எஃபெக்டிவ் நியூக்ளியர் சார்ஜ், screening effect. These are the terms you have to use. so due to the lanthanide contractions completely decreases, so that it causes zirconium hafnium similar atomic radii, niobium and tantalum and molybdenum so similar atomic radii, okay. so this is your another one question, okay. after that, that is this is for exceptional cases, scandium, yttrium, lanthanum, as usual down the group atomic number increases, atomic radii increases. Where it decreases, started from lanthanum, okay, because of this is 4f intervening of 4f electrons, okay. after that melting point and boiling point, melting point and boiling point. listen, so here melting point, boiling point and atomization of enthalpy, very very important, okay. atomization of enthalpy. so here the melting point, transition elements having very high melting point and boiling point and high atomization of enthalpy, okay. so here we can speak in terms of atomization of enthalpy, that is before that I explained this is nucleus and this is n-1d subshell, n-1d subshell. listen, this is n-1d subshell and this is ns, okay. so this energy gap is very small, okay. so because of the incoming electrons directly entering to the s orbital outermost as well as the d orbital, So these two energy gap is very less. So both orbitals can take part in a chemical bonding. Okay, so that is the unique character, special character. So the d block elements, it high melting point, boiling point. So the interatomic bonding takes place. It is due to the presence of partially filled electrons of n minus 1d. Okay, in the first point, partially filled n minus 1d orbitals. Second one, the energy gap is very less. After that, the third one, the presence of unpaired electrons. Okay, so whenever like that question asking why transition elements have a high melting point, boiling point and high atomization of enthalpy, so immediately the melting point and atomization of enthalpy directly proportional to the presence of unpaired electrons. Okay, so unpaired electrons, these are the terms you have to use. So if unpaired electrons is present, because of this energy gap, the unpaired electrons present, the strong interatomic metal bonding takes place. In the second point, strong interatomic metal bonding. Okay, metal bonding takes place. So strong interatomic metal bonding, the metal bonding, so it is a high atomization of enthalpy. Okay, so what do you mean atomization of enthalpy? Suppose it is iron. Okay, iron. So we have to break record of energy need to break this bond. That is, if it is present more, then how can we separate for iron and iron? So that the presence of it, the term we can use the presence of unpaired electrons. Those elements, it undergoes strong interatomic metal bonding. Stronger the metal bonding, higher the atomization of enthalpy. Okay, so this atomization of enthalpy is more in 5D series, greater 4D and 3D series. Okay, so which one is more? 5D series. So the 5D series, you see here, that is a coinage metal. What are the coinage metal present? Copper, this is your question 1. Copper and silver and iron, that is gold. This is noble elements. Why it is noble elements? Because of high atomization of enthalpy. Okay, so after that, in your book concept, NCERT concept, the tabular column, the physical property is given. Among this 3D series, the atomization of enthalpy is vanadium. Okay, after that titanium. Okay, you keep it in your mind. TV, vanadium and titanium. So vanadium, it is a packed. So see here, why it is HCB? I wrote here, I have written HCB because of it is a solid form. It contains the what is that? The arrangement of lattice. Okay, HCB means hexagonal close packing. Okay, for this all the 3D 4D, this is a HCB and this is hexagonal close packing arrangement. BCC means a solid state we are going to study. There are 3 types of that is body centered cubic and face centered cubic. Okay, so that we have to study later. So this is for body centered cubic the arrangement. Okay, so manganese, why here I have written into, there is no it doesn't have a lattice structure. Okay, manganese, it doesn't have a lattice structure, proper lattice structure. Okay, and the arrangement இல்ல. இதுக்கெல்லாம் பார்த்தீங்கன்னா closed packed, அப்புறம் BCC அந்த மாதிரி ஒரு நல்ல arrangement, lattice packed arrangement. Atoms or ions arranged in a manner, no? So for 3-dimensional shape, that is we called lattice. So here இந்த manganese-க்கு வந்து சரியான இது இல்ல, சரியா? அதனால தான் into mark. அதே மாதிரி zinc, cadmium, mercury-க்கும் வந்து என்னது, there is, it doesn't have any proper structure. Okay, so that we cannot consider this is a pseudo transition elements. Okay, pseudo transition elements means it is a completely filled, there is no possibilities for transition series. Okay, so here, so that it is a high come to here for that concept, high atomization of enthalpy, copper and silver and silver and this is for iron, gold. Okay, and melting point, boiling point. Zinc is a low melting point. Zinc is a low melting. Why it is a low melting? There is a no crystal arrangement, crystal lattice. Then it is a low melting and boiling point, highly volatile, easily volatile. Okay, so this is your melting point, boiling point. Okay, and another one concept I want to say, that is this energy gap is very less, so that these transition elements show special characters. So most of the elements are that is colored in nature. Okay, colored form. Okay, so colored form. And second one, so it act as a complex formations, complex form. And third, complex form, and it shows variable oxidation state, and it forms alloys, and it acts as a good catalyst, and sixth, it is used for interstitial compounds. Okay, because of, so already I said this is a ns n minus 1d gap is very small, it's a energy gap small, so both the orbitals can take part in a chemical bonding, so that the special characters, it shows variable oxidation state as well as alloys, catalyst, interstitial. You see that most of the elements are used for catalyst. Okay, vanadium is a good catalyst, molybdenum is a catalyst, iron is a catalyst, cobalt is a catalyst. Okay, so what is the catalyst? To speed up the reactions. Okay, because of this energy gap is small and low shows a variable oxidation state, so that the characters are unique compared to non-transition elements like S block elements and P block elements. Okay, here you see that colored. So most of the elements, it contains unpaired electrons. So already I taught the unpaired electrons means, suppose one unpaired electron is present means, so this unpaired electrons, it goes excited state. Okay, excited state. So it absorbed some energy and it goes to excited state. This excited state, it is not stable. So when it is not stable, immediately it comes back to the ground state. So that time that it emits their light. So in our the eyes, it is a visible region, it looks different colors. Okay, so that the presence of so where the, whenever the question asks you colored property, immediately you said you used this word unpaired electrons. Unpaired, presence of unpaired electrons, that is a paramagnetic behavior only. It proves the colored compounds, colored in nature. Okay, so complex formations, because of partially filled the d orbitals vacant site present. So this only we studied in our coordination compounds. Ligands donate a pair of electron to this vacant site to form the complex formations. Okay, so variable oxidation state, because of this energy gap is less, it shows variable +1, +2, +3 and so on. The osmium is a very high oxidation state, that is 8 + 8. It is a very important concept. Many times in this question as a O4 osmium tetroxide, this is a +8 oxidation state, highest oxidation state. The manganese, it is a +7, after that it is a +8 oxidation state. Okay, so that because of the reason is a gap is very less. Okay, and partially filled electrons. Okay, and alloys, why it is alloys formations? It is a smaller size, so easily fit into the one element to another element to form a new mixtures, homo or hetero mixtures. Okay, so homogeneous mixtures, no, so alloys, that is it forms a alloys. Okay, so the reason smaller size, okay, partially filled n-1d orbitals, so that it forms a alloys. Catalyst already I taught, interstitial compounds also. Okay, so this is for your special characters of why we need to study for this transition elements, because of these many special unique characters, so that we are studying this transition element series. Okay, after that ionization enthalpy. Okay, right. Friends, next trend, ionization enthalpy. Okay, we very well know that ionization enthalpy is the energy required to pick up one electron from the last valence shell electron. Okay, last electron. Okay, so that is ionization enthalpy. So this ionization enthalpy depends upon nuclear charge, effective nuclear charge. Okay, so usually the left to right ionization enthalpy increases due to because of atomic size decreases. Why it is decreases? Because this is 21, atomic number 22, 23 and so on. So added electrons add to the same penultimate shell. Okay, so that is completely the size would become decreases because of the effective nuclear charge between the nucleus and the shell. Okay, so the size become decreases, ionization enthalpy increases. Okay, for this case 3D series scandium to chromium and iron to copper. So this ionization enthalpy increases. Okay, so because listen, for m plus 1 compared to m plus 2. Okay, for this is compared to plus 1 state, plus 2 state is a stable. It is a stable. You keep it in that. Very very important. Stable. So you the scandium to chromium and iron to copper, it is increases. It is a exceptional case. Typical manganese and zinc. Okay, because of manganese plus 2 state, that this is a configuration is 4s2 3d5 4s2. Okay, zinc 3d 10 4s2. This is half filled electronic configuration, this is full filled electronic configurations. Okay, so we cannot pick up one electron from the last shell. It is a half filled stable configurations and full filled stable configurations. Okay, right. So this IE2 for manganese and zinc is a typical one. For IE3, what is that configurations? 3d6 4s2, 3d6 4s2, iron 26, no, 3d6 4s2. For iron 3, here one electron and here one electron, that is 3d5. So 3d5 half filled, we cannot remove easily. So this is a typical state for scandium. IE3 is a typical for iron. Okay, after that nickel, copper, zinc, it is the IE3 is increases because its oxidation state is the plus 2. Earlier I told to you, compared to plus 1 state, plus 2 is a stable. Okay, so nickel 2 plus, copper 2 plus, zinc 2 plus, it is a stable form. So that IE3 the for this ionization enthalpy is more. Okay, so ionization enthalpy na ஒண்ணு இல்லமா, இது வந்து NS cell, it is n minus 1d cell. இதை நல்லா ஞாபகம் வச்சுக்கோ. NSல 2 எலக்ட்ரான் இருக்கும், n minus 1dல 1 to 10 எலக்ட்ரான் இருக்கும். இப்போ இதில் ஃபஸ்ட் அயன் IE1 அப்படின்னோன்னா ஒரு எலக்ட்ரான் ஃப்ரம் திஸ் s ஆர்பிட்டல். IE2 அப்படின்னோன்னா another one electron from this s orbital. IE3ங்கிறது வந்து என்னன்னா the d orbital இருந்து ரிமூவ் பண்ணுறது. ஸோ it may be half filled or full filled அப்படின்னா it is not possible. It is a typical state. Okay, we cannot remove easily. So this is for ionization enthalpy 1, 2, 3. Okay, so here okay, that's all. Next class we will continue.